Hi everybody, my name is James Allison and I'm a researcher here at the University of Oxford. In this lecture I'm going to talk about some of the more advanced techniques and concepts that we use to generate images from radio interferometers. Before I move on with the lecture, I just wanted to give my thanks to Jack Radcliffe and some of the other people mentioned here who have really prepared most of the material for the slides that I'm going to show you. So what are the topics we're going to cover in this lecture? Well, here's a summary of what we're going to talk about. So the first thing I'm going to do is sort of recap the concepts of clean, which you've already covered in a previous imaging lecture, but I'm just going to go back over that. And I'm going to talk about some of the other methods that you may want to use and when to use them, particularly when you've got extended emission and you want to think about using sort of multi-scale methods to be able to deal with that. I'm also going to talk about some of the effects of non-coplanar baselines and wide field imaging. So as yet we haven't really talked about the W term, dealing with the W term and solutions for being able to deal with wide field imaging. I'm also going to talk a little bit about when you have a wide band, so when you're doing multi-frequency synthesis and looking at deconvolution when you're thinking about what the spectral dependency is of your sources in the field. So the function as a function of frequency and trying to recover some of their spectral behavior. And then also how you use the clean components then to construct a model to be used in self-calibration, which is very useful. One of the other aspects of imaging, of course, is not just looking at deconvolution and the point spread function, but also looking at the primary beam attenuation and correcting for that, and how that's then used in mosaicking individual pointings, individual fields together to map out a wide field image. And finally, I'm going to talk a little bit about some of the issues around direction-dependent imaging. Okay, so let's start. So the first thing I want to do is really talk about the fundamentals of how the visibilities are actually related to the image, which you've already discussed previously, but it's good to recap on this. So of course, the key equation is this one shown here in the top of this slide, which shows how the visibilities V are related to the image I by this somewhat complicated equation given in terms of these coordinates U, V, W, L, and M. Okay, so what we see here is actually a somewhat idealized version of this relationship. This is kind of the relationship between the continuous variables. Of course, the interferometer itself measures a sampled, sort of discrete sampling of the visibilities. It doesn't measure continuously all of the visibility domain. And likewise, it also has a lot of noise associated with the fact that we don't have infinite signal to noise in our data means that we always have some error associated with the visibility measurement, which may be dependent on U, V, and W and the baseline distances. So we do have to take that into account as well. However, this is the sort of relationship between these two quantities that we see in this equation. And so U, V, and W, as you know, are the coordinates for the interferometer's geometrical vector. Basically, U and V form a plane that is perpendicular to the direction to the source, whereas W is the component in the direction of the source. And L and M, which define the position on the sky, they're the direction cosines, they define the position, the angular position within the image I. And what we want to do is we want to calculate the image I from our measured visibilities V, and that is what we're trying to achieve with imaging. So in order to reconstruct I, to recover the image from our visibility data, we have to invert this quite complicated equation, which is actually quite difficult and computationally expensive. However, we do have one advantage when we have small images, when we have small fields of view. And that in that case, the L and M coordinates, so the angular position away from the phase center, become quite small. And so we can effectively ignore these L squared and M squared terms in this equation. So they drop out, they become 0. And likewise, the component in the direction of the source from the interferometer, from the baseline plane of the interferometer, that also tends to 0. And when that happens, so for these small fields of view, we get this second relationship, this approximate relationship given by this equation here. And this relationship is actually the two-dimensional Fourier transform of I. So V is now given approximately by the two-dimensional Fourier transform of I. And this means that we can now just take the inverse of the right-hand side to recover the left-hand side, to recover I. And so we just have to take the inverse of the 2D Fourier transform, which is an algorithm that we can do. And so that theoretically is how you recover the image from the visibilities. You take the two-dimensional inverse Fourier transform of the visibilities, and from that you recover your image for small fields of view. However, of course, in practice it's more complicated than that because, as I've already said, the interferometer samples the visibilities. So first of all, we don't have a continuous measurement of the visibilities on all spatial scales. We have a sampling of them on various specific spatial scales. And there are a lot of practical considerations then to reproduce a nice image of the object that you're looking at. So as an example, we're going to consider Messier 82, this object here. This is a starburst galaxy. What you see here is a composite image. This is not a radio image, but you see a composite image of the optical, infrared, and X-ray data. And you can see you've got this beautiful galaxy here, which is thought to have been recently undergone some sort of merger, in the past, in the recent past. And this has triggered a starburst. And you see these beautiful bipolar outflows triggered by this starburst activity in this galaxy. Now, a starburst will generate a lot of radio emission through supernovae and through H2, just star formation that occurs in this galaxy. And so this is what we see in the radio, and this is a beautiful image here. So how does one produce such a nice image from our interferometric data? And it's quite a complicated process. So if you just look at the two-dimensional inverse Fourier transform with the visibilities, this is the sort of image you get. This is called the dirty image. And this is data from the Very Large Array in New Mexico in A configuration. That's the most extended configuration of the array. And you can see that this dirty image, as it's called, has a lot of structure which is not actually real, not astrophysically real, and it's a result of this finite sampling of the visibilities. And the Very Large Array has a Y configuration, and you can see that's been imprinted in the point spread function. So you can see that this in this image we've got several very bright point sources which are convolved with the point spread function of the telescope, and that's what you're seeing here. And so really one of the key aspects of doing imaging is to actually see how we can deconvolve this image from the point spread function in order to reproduce a nice high surface brightness sensitivity reconstruction of the image. Clearly then we want to remove the effect of this dirty beam, this point spread function, from our image. And so in order to do that, we need to use an algorithm called a deconvolution algorithm. Now, the most commonly used deconvolution algorithm is CLEAN. And CLEAN was invented in 1974 by HÖGBOM. And at its fundamental level, it's quite a straightforward procedural algorithm. And the way it works is like this. First of all, the brightest peak and its strength is identified in the image. That is then multiplied by the known point spread function, because we know what the point spread function is for a radio interferometer, because it's simply just given by the inverse Fourier transform of the sampling function. And we take that product and we multiply it by the gain, the loop gain. And the loop gain is just some factor, normally about 10 or 1%, depending on how accurate and long you want the algorithm to run for. And once we've got that, so we've got the brightest peak strength multiplied by the point spread function, multiplied by this gain, we then subtract that from our image. And we store that subtracted component we store in a two-dimensional model, which we call the CLEAN model. And now what we do is we repeat that step. We go back to step one, we identify the next brightest peak. It may still be at the same position, of course, because we've only subtracted a small fraction from it, or it might be at a different position depending on how our object is structured. And so we perform that step again, and slowly over time we build up a CLEAN model, and we slowly subtract out the point spread function convolved with our signal. And so what we end up with is a residual image, which is basically something noise, low-level signal and noise convolved with our original point spread function, plus our CLEAN model. And then finally what we need to do is reconstruct the CLEAN image. And so to do that, we take our CLEAN model and we convolve that with what's called the restoring beam, or the CLEAN beam. And the restoring beam is just a nice representation of the resolution of the observation. And normally that's done by just fitting the main lobe of the point spread function with a nice Gaussian, with no side lobes, none of this sort of structure that we saw in our dirty image. And so we convolve our CLEAN model with that nice beam, and then we add it back into our residual map to produce our final CLEAN map. And we should end up with a nice clean representation of our source. And so here's what we get when we apply this Hogborn clean algorithm to our data for M82. And so you can see now that a lot of the original structure from the point spread function that we saw before has been removed, it's been deconvolved, and the point sources have popped out from regions of high star formation, and then you can also see this extended emission as well that's starting to appear. But you can also see that there's still some of the artifacts left in there from that have been from the convolution of the remaining signal that hasn't been cleaned with the point spread function, and you can see as well that we've got this sort of these broad stripes as well in the residual map, which are an artifact of the extended emission. So what does our clean model look like? So the components that we've managed to identify and remove from the residuals during clean, well, that's what this looks like here. So as you can see, as I've already said, the clean model basically comprises is a two-dimensional model comprising delta functions at positions in the map, and you can see that here. So you can see the points. The point sources are indeed represented as points, but likewise the extended emission as well has been mapped out as a sort of an extended distribution of delta functions. And so you can see that the extended emission is not being represented as a sort of smooth function spatially. It's being represented as a sum of delta functions, which in itself is not an accurate representation, reproduction of what the emission looks like. Now, since, of course, the original clean algorithm was invented in the 1970s, there's been a lot of development since then to improve on it. And we have some examples here of other options in clean in deconvolution that you could use that are commonly used now. So we have the first example here is what's called the maximum entropy method. Now, this is quite different to the procedural clean algorithm that I just described. This is a very different sort of algorithm. What it does is it's a Bayesian method, and it maximizes what's called the entropy, which is a quantity that depends both on the image data and also a prior image that you give it, a sort of a description of what you think the image should roughly look like. And of course, then your final image is going to be biased somewhat to looking like that. But if you have some prior understanding about what your image looks like, for example, through a lower resolution image or just some sort of source model you know about this object. So we know, for example, with M82, we know there's a galaxy there, right? So we might give it that information. So maximum entropy maximizes the entropy quantity subject to the constraint of minimizing a chi-squared statistic based on the model visibilities. And so it's those two constraints. Essentially, it's a penalized fitting method which allows it to reproduce a model of the sky deconvolved from the point spread function. And so you can see the results of this here. One thing you might notice, of course, is there still seems to be some structure associated with the point spread function. So deconvolution hasn't worked particularly well. And in particular as well, you see that some of the more extended emission hasn't been recovered. You can fine-tune maximum entropy, as I said, using a prior model. If you use a flatter model, you may be able to recover more of the extended emission. The problem with MEM is that it's agnostic about the spatial scales in the data. So if your data are distributed to much longer baselines, such as in the VLA array, then maybe you don't recover as much of the extended emission, which is maybe what we're seeing here. Another version of clean is what's called Clark clean. So Clark clean is an extension of the original Hogborn algorithm. What it does is it constructs an algorithm from a set of minor cycles and less frequent major cycles. Within each minor cycle, it implements the Hogborn clean. So it just carries out that algorithm to produce, after a number of iterations, it produces a clean component model and the residual model that you get from Hogborn clean. And then it carries out a major cycle. And in that major cycle, it takes the clean component model, it further transforms that to construct the model of the gridded visibilities. It subtracts that from the gridded visibilities to produce a new residual image. And then that residual image is then cleaned again in a minor cycle for several iterations to then carry out another major cycle. And it continues to do that until you produce a reasonable image, which is like the one we see here. And you can see that it's improved upon the original Hogborn clean, but there's still some artifacts associated with the extended, more diffuse structure, which you can see in this sort of banding across the image. Clark-Stokes is an adaptation of that, taking into account the Stokes information, so the Q, U, and V information, so the polarization information on the sources, because that allows you to better identify real signal in the data, devoid of sort of the artifacts that you get from the point spread function. So clearly, diffuse structure is causing a few issues with these clean algorithms, and there was a new algorithm that was developed by Tim Cornwell in 2008 called multi-scale clean to kind of deal with this problem. So the original clean, as I mentioned, constructs a clean component model out of basically delta functions, so pixels within a clean component image. And so what multi-scale clean does is to, rather than use not just delta functions, it tries to fit during the minor cycle smooth Gaussian kernels of a sort of finite extent to kind of create a more sort of smooth diffuse structure, typical of what you'd see in extended emission in a radio source. And so you can you would normally tell the algorithm when it's implemented, say in CASA, the sort of scales that you'd like it to fit to, and typically as sort of integer scales of the point spread function. So what does that look like? Well, when we apply that clean to M82, well, that's what we get here. And you can see now that the extended emission is reproduced nicely, and you're seeing less of this banding across the image due to artifacts associated with cleaning an extended structure. So multi-scale clean has really made a much nicer image here with M82. So what does your clean model look like? Well, this is what it looks like here. And you can see straight away that it's no longer a summation of delta functions. It's a nice, smoother image, smoother model from the sort of linear combinations of Gaussian kernels of different scale sizes. And so you're nicely reproducing that extended emission. Okay, so we've considered some of the deconvolution algorithms available there. I'm now going to revisit something that we kind of ignored when we talked about doing the two-dimensional inverse Fourier transform, but I'm now going to go back to that, which is the problem when you have a wider field. So when you don't have a single object like M82, which we've just looked at, but you actually have a much wider field with multiple sources in it. And by wide field, what I mean is really that the field of view, the size of the field you're imaging, is much larger than the point spread function, which is defined by your longest baselines. And so in that case, we can no longer really ignore the W term. So this is the component of the interferometric geometrical vector in the direction to the source. And the problem there is that the visibility volume is no longer easily described as a two-dimensional. It's no longer a simple two-dimensional Fourier transform between the visibilities and the image, which is where the image is defined by the cosine the direction cosines. And so, if we were to just take the inverse Fourier transform of the visibilities, rather than recovering the correct image, we would end up recovering what's called the three-dimensional image volume, which is not really physical. It's not described by as a two-dimensional image with direction cosines on the sky. And in fact, we have to think a bit harder about how we might deal with that situation. So looking a bit closer at what's going on here, so you can see in this diagram, we have M and L, which are your direction cosines, which tell you the position on the sky of your source brightness distribution. And then we have this N component, which is kind of a position within the three-dimensional volume. And so if you take the inverse Fourier transform of the three-dimensional visibilities, you end up constructing a sort of three-dimensional image on the surface of the sphere, which you can see here. And so what we need to do is we need to somehow take those solid stars and project them into their correct position on the tangent plane, where the tangent planes is the tangent plane to the sphere, the surface of the sphere at the position of the phase center. And so how do we actually achieve this? Well, there are two approaches. So the first is a technique called faceting, and this is quite straightforward. What this basically does is it breaks your image down into multiple smaller images, where those smaller images have a field of view that is small, where you can ignore the W term correction. And so we just get to ignore it like we did before. And then at the end, we just stitch together these images to form the final image. So that's a quite straightforward approach. But a more common approach that is used these days is something called W projection, which effectively performs this procedure of taking those stars, those sources that are on the surface that you can see here, and projecting them to their correct position on a two-dimensional image at the tangent plane. And both these approaches are available in the CASA software, and we'll just talk a little bit more about them now. So firstly, faceting. So as I've said, faceting is a way in which you basically break down the image sphere into smaller subfields, so smaller tangent planes, which then you can then use to straightforward two-dimensional inverse Fourier transform, and then stitch together the final image. Now, of course, you may know where sources already are, known sources already are, so you may want to position your facets such that they do cover those known sources, and obviously that's important to get a nice image back. You also want to choose enough facets that you can sort of more accurately reconstruct the image from the image sphere. And the other thing, of course, you might want to consider is that you want your facets to overlap so they complete full coverage of the primary beam. Alternatively, we can use W projection. So W projection, effectively, we break down the three-dimensional visibilities, which have UV and W coordinates, into a series of W planes. And so we can specify how many planes we want. And for each of those W planes, we project those visibilities onto the W equals 0 plane using this relationship given in this equation. And then what we do is we take the inverse Fourier transform of that convolution in order to recover the sky brightness distribution, I as a function of the direction cosines L and M. And so we end up with our dirty image with the sources at their correct positions. However, there's a complication associated with doing this algorithm, and that is that the point spread function, so the dirty beam, is no longer a constant over the image, but actually changes with position. And so we have to deal with that correctly when we come to do our deconvolution. And we have to do that using something called the Cotton-Schwab algorithm to do that deconvolution. So separating the point spread function from the dirty image to produce a nice clean image. Cotton-Schwab is a variant of the Clark-Kleene algorithm. So the Clark-Kleene algorithm, as I mentioned before, has this major cycle where you subtract the clean model that you've constructed using the HÖGBOM algorithm from your gridded visibilities. In the case of the Cotton-Schwab algorithm, rather than subtracting them from the gridded visibilities, which is basically the Fourier transform of the image, you subtract it from the original visibilities measured by the telescope, so the ungridded visibilities, and that's a more accurate representation of the visibilities. And so you don't get the various gridding effects associated with that approximation. And so by combining that with the W projection algorithm, so one of the great things about Cotton-Schwab is that it can be operate on multiple fields at once, and so it allows us, we basically run a clean algorithm on multiple fields from this W projection algorithm, the W planes. This allows us to deal with this varying point spread function with position. And so it looks very similar to the Clark-Kleene algorithm. You basically do the same HÖGBOM minor cycle where you find a peak, you subtract the PSF multiplied by the peak with the small gain. You do that until you get to about 80-90% of the highest peak that you're multiplying by, and then you take a major iteration by doing the subtraction from the ungridded visibilities, and then you continue to do the minor cycles and major cycles again. And once you've done that, you should end up with an image that is both clean and deconvolved from the point spread function, and that is devoid of the effects of ignoring the W term, because we've now correctly dealt with that. So I'm now going to show you what I mean when I talk about either ignoring the effects of W term or correcting for it. Let's now consider an example of when we might want to use W projection to correct for the W term in wide field imaging. So here we have an example observation of the Goods North field using the E. Merlin telescope, which is a sort of mid baseline length interferometer in the United Kingdom. And what we have here is an example image where we have two sources. We have one source that's fairly close to the pointing center, and we have a source that's much further away. And we can imagine that we're probably going to want to have to deal with the W term, the wide field imaging effects, for the second source, which is much further away than the face center of the image. So if we just look at the first source, as we suspected, actually it doesn't make much difference at all whether you use W projection or not. The images look pretty identical, and the small field approximation holds. So we can just take the Fourier transform, the inverse Fourier transform of the visibilities, and construct an image. However, as we suspected, when we look at the second source, which is much further away, so its distance from the phase center is much greater than the size of the point spread function, which is given by this little white ellipse in the bottom left-hand corner of the image, you can see that there are far more errors associated with this source, the position of this source, when we don't use W projection. And what's happening there is the source is sort of moving around in the image because it's not correctly being projected to the right position, and so you get this sort of smearing out of the source, which is what we see here. Whereas in the right-hand panel, where we've actually correctly dealt with the W term, with W term projection, we have a much nicer image. And so this really demonstrates then why we want to do this. In addition to considering the effects of wide fields when you're imaging, you also want to consider the effects of wide bandwidth. So that's when your fractional bandwidth, so the size of your band is considerable compared to the frequency that you're observing at. And in that case, what you want to do is you want to grid your visibilities at different frequencies onto the same UV grid, like we see here in this right panel, when you're forming a single continuum image. And so then that you produce an image that is representative of the visibilities over that full band. And in addition to using multi-frequency synthesis to construct a single continuum image from your visibility data over a wide band, you may also want to use the information that you have, the in-band information you have from this wideband data, to be able to understand something about the spectral behavior of your images, your sources. And so this is done using something called multi-term multi-frequency synthesis. And so in this case, what you do is you approximate, so rather than assuming a flat spectrum, so essentially flattening all that information into a single image, you can approximate the spectral behavior using a Taylor term expansion about a reference frequency, which is given by this equation here. And so you can then use these Taylor terms, actually assuming a model for your source that's based on, or your source is based on a power law spectrum, in order to recover things like the spectral index and the curvature of the spectral behavior of your sources using these Taylor term images. And this is very useful, of course, when you have very high dynamic range and sensitive observations over a wide band, to be able to recover the spectral behavior of your sources. And this is also incorporated into CASA as part of its multi-scale clean. Now, previously in another lecture, you will have covered the concept of self-calibration. So the idea of self-calibration is obviously, when we want to calibrate our visibilities, what we want to do is we want to correct for any frequency and time dependency of the telescope response to the sky, so that we end up reproducing the correct sky brightness distribution from our visibilities. And so the first step towards that, of course, is to observe our standard sources, so our primary and secondary calibrators, in order to sort of correct any coarse behavior and correct for the flux scale. But once we've done that, we still may have some time variation within the observation of our target field that we should probably correct out. So the antennas will the antenna gains will vary through the observation of the target field. And so to correct for that, we use a technique called self-calibration. And so self-calibration is you have your observed visibilities, you do some imaging, you then from your images construct a model of what the sky looks like, and then from that you can then further transform that model. Then you get a set of model visibilities, which you can then use to calibrate the gain matrix. Because you can then say, well, okay, this is what the visibility should look like in my model, and this is what they don't look like, and so I can then correct the antenna gains to be able to improve the observed visibilities. Now, and then you can iterate on that process through several loops and see whether it converges to a reasonable solution. So you should see your phases, of course. For a point source, you should hopefully see your phases converge to zero for a point source at the phase center, but obviously for a complex field, you just need it to converge to something that the model doesn't change each time. So an obvious choice, of course, for your model that you might use in self-calibration then is the clean model. So the clean component model that's generated during the deconvolution. And so that then can be fed into the self-cal loop iteratively to calibrate the self-calibrate the image. So how might you implement this in reality? Well, of course, you want to do a few steps. So what you would normally do is you do your phase-only calibration, followed by a sort of shallow clean, which would avoid any clean bias and sort of, you know, accidentally including artifacts from the sort of poorly calibrated image into your clean model. So you do a shallow clean to capture sort of the bright things to begin with. Then you feed that into a phase-only self-calibration, and then get a nicer image out with fewer artifacts. And then you do a deeper clean to get a more accurate representation of the sky model. And then that would be fed back into self-calibration, maybe now including an amplitude and phase self-calibration. Do a further deep clean to recover your sort of final nice image that you want. See in this image, it reconstructs the extended structure quite nicely. Now, rather than just being a sum of delta functions of point-like sources, it's now you've got this nice smooth extended structure, and it looks like a really nice image. Okay, so another consideration in radio astronomy imaging is what's called the primary beam correction. So we've already talked about previously about the point spread function, otherwise known as the dirty beam or synthesized beam, and that's your resolution element. So that limits the resolution of your image, and that's defined by both the sort of distribution of baselines, so the longest baselines in your array, plus also the weighting that you've applied to the visibilities when you form the image. But there's another type of beam called the primary beam, and the primary beam is the field of view of the individual elements in your array, so the individual antennas in your array. And so when you construct an image and you do the deconvolution, so you're left with a nice clean image, your signal, so the flux densities that you measure as you move away from the pointing center, are attenuated by this field of view, by this primary beam. And so you need to correct for that. You need to multiply by the inverse primary beam in order to be able to accurately reproduce the flux densities of sources away from the pointing center. And so obviously for total intensity, this would just be a single correction, but a scalar. But for polarized emission, of course, where you've got 4 Stokes parameters, this would actually be a matrix that you'd multiply it by. And here's an example of what a primary beam might look like. So you can see in the center of the image, so at the pointing center, the main lobe is nicely sort of Gaussian-like. It's fairly straightforward to model, and so to correct for and accurately reconstruct the flux densities of your sources. But as you go further out in the image away from the pointing center and you go into the sort of side lobes of the primary beam, you can see that this might get a lot harder to model accurately. And as you get further away, of course, your accuracy, the error that you may introduce into your flux densities of your sources is going to increase, because the factor that you need to multiply each source's flux density by becomes larger. So this is not a trivial issue for when you're trying to make wide field images and look at sources well away from the pointing center of the telescope. And here's an example of an image that's now been primary beam corrected. So in a dirty image or in an uncorrected image, what you'll see is sort of even noise. You'll see even noise across the image, but you'll see bright sources in the center and fewer bright sources away from the center, of course, because they're being attenuated by the primary beam. But the noise will be flat because the noise in that case doesn't really depend to first order on the position in the image. However, once you've applied the correction, you're obviously multiplying up each position's, the factor by which each position's flux density is multiplied by depends on the primary beam. And so as you go to greater distances away from the pointing center, everything gets multiplied up, including the noise, which is why you see here that the noise increases rapidly towards the edges of the image. And one thing you have to watch out for is the primary beam actually is a function, or can be a function, of time and frequency. So the primary beam scales as lambda over d, so as does everything like the resolution. And so you do need to worry about when you have a wideband image that what the factors by which you correct for the primary beam. The other thing as well that you have to worry about is that the primary beam isn't necessarily axisymmetric, so can rotate with respect to the sky over time, depending on the telescope you're using. If it's not got a fixed position angle with respect to the sky, then sources at the edge of the field can rotate through fluctuations in the primary beam attenuation, which can manifest as what look like variable sources and also affect the accuracy to which you can measure the flux density of those sources. So you have to be careful to make sure that you model that time variation properly. Of course, as well, that the primary beam response of the telescope can change over time as well. So holographic measurements need to be taken over a reasonably regular basis to make sure that that's captured properly. So here's an example of the primary beam spectral variation from the UK Lovell telescope across the 1.4 to 1.6 gigahertz band, and you can see that obviously it scales as lambda over d, and so you're seeing quite a significant variation in the field of view with frequency. And so that needs to be taken into consideration when you're, for example, doing multi-frequency synthesis, that you are accounting for the fact that your primary beam correction could change as a function of frequency. Okay, so another related aspect of imaging to the primary beam correction is the fact that, for example, if you have an image here where your field is focused on the source to the left, but there's this FR1 galaxy to the right over here, that it may well be within the side lobe of the primary beam, which isn't really ideal for imaging that FR1 galaxy to the far right. And so to be able to deal with that, of course, what we want to do is we want to construct multiple sequential images across that field. And so this is done using a technique called mosaicking, where we undertake multiple pointings with the telescope and then combine them with the correct weighting. And so what is that correct weighting that we should apply for these individual pointings to produce this single wide image? Well, what we want to achieve in our final mosaicked image is the image with the best possible signal to noise on the radio emission that we want to study. And in order to do that, if we assume that each of our individual fields have the same underlying noise, then we want to weight by the primary beam squared to get the best possible, this is the optimal signal to noise out. And this is just a standard inverse variance weighting scheme. If our individual fields have different noises, so different underlying noises, then we need to adapt that scheme to account for that as well. So obviously we want to use mosaicking to reconstruct an image that contains multiple pointings from a series of observations with a telescope. There are some telescopes that actually are equipped with what are called phased array feeds that allow you to be able to simultaneously observe a wide field of view at once. So for example, the Australian SKA Pathfinder ASCAP has these phased array feeds which allow it to sample the focal plane and actually simultaneously produce a 36 pointing set of observations which you can then mosaic after the fact to form a 30 square degree field of view image. But this still requires you to actually do the mosaicking. It doesn't produce the mosaic for you when you invert the Fourier transform. You still have to do the mosaicking task, but it means you don't have to. It means you can rapidly survey. You don't have to undergo multiple pointings with your telescope. You can just do it in a single pointing. So finally, one of the things we've ignored so far is the effects of direction-dependent calibration, and this means that so far we've assumed that the calibration solutions that we're applying that are required are constant across the whole field. So when we solve for our gains using self-calibration, we assume that the model is fine for the whole field, and we apply a single correction to that field. Now there are certain scenarios where that assumption is not necessarily true. So, for example, if you have a large spacing array where the atmosphere that elements of that array see are different, and affects the calibration differently, then, for example, at low frequencies, the low-FAR array, the ionospheric effects for widely spaced elements may have a significant effect that require direction-dependent calibration. And so there are a number of ways of dealing with this problem where you need to apply a calibration solution depending on the position within your image. These include faceting, which breaks the field down into a series of facets in a similar fashion to the way faceting is used for the W correction mentioned earlier. So you take your image, you break it down into multiple smaller components called these facets, and then within each individual facet, you solve for you self-cal, you solve for the calibration, and you apply this constant calibration to that facet. And so the accuracy of your direction-dependent calibration, of course, depends on the number of facets that you adopt, that you break your image down into. And you may also choose your facets such that they encompass particular sources in your field as well. You obviously don't want a very bright source to be kind of between on the boundary between two facets, for example. In addition to that, we have peeling. So peeling is where you identify your bright sources in your field, and you rotate to those sources, you self-cal on them, and then you clean and you subtract out the model, and you're left with a residual model with the nicely peeled away bright source removed, and you continue to iterate that on the less bright sources, and then reconstruct a nice calibrated image from that. And there's a number of other approaches that can be taken as well. Okay, so that's the end of our lecture. Just to recap some of the topics I've discussed. So I started off talking about clean and some of the different deconvolution methods that are used in clean. And I also talked a little bit about when you have extended emission, you want to use an approach called multi-scale deconvolution, which allows you to recover the more diffuse extended emission that you might get in some sources. I then moved on to wide field imaging, where we have to consider what's called the W term, and we can no longer use the small field approximation for recovering the image from the visibilities. And I talked about some of the solutions there that you can use to do that. I then moved on to looking at wide band effects, so moving away from wide field to wide band, looking at multi-frequency synthesis, and also when you want to recover the spectral behavior of your sources, so the spectral behavior of the sky brightness, by modeling that as a sum of independent Taylor terms. Moving on from that, I talked a little bit about how you can use the clean components that you get from the deconvolution process to improve your calibration solutions through self-calibration. I also talked about the primary beam correction, so the fact that your telescope obviously has a response as a function of position in the image that attenuates the signal, and how you need to obviously accurately know what that is in order to reconstruct the actual flux density of your sources at positions away from the center of the image. And related to that, of course, when you want to construct a larger image from multiple individual pointings using mosaicking, how you go about doing that using the information you have on the primary beam. And finally, I talked a little bit about the direction-dependent effects, particularly when you can't just apply a single calibration solution to the whole field, particularly when your array, for example, elements of your array might be seeing different effects in the atmosphere independently of each other, and you do need to then apply a direction-dependent calibration. Okay, well, thank you very much for listening, and I hope you enjoy the rest of your lecture course in radio astronomy. Thank you very much.